Okay, this is Chapter 10, Redox Lesson 1. In today's lesson, we are going to define oxidation and reduction, learn how to recognize oxidation and reduction, and we'll do a brief overview of assigning oxidation numbers. The actual rules will follow in the next lesson. Reduction and oxidation reactions. So we get the redox from the RED in reduction and the OX in oxidation, and we come up with redox. These are reactions that involve the gain and loss of electrons. Gain and loss of electrons, which I will abbreviate E minus. Sometimes this is called a transfer of electrons. Oxidation must occur simultaneously, meaning at the same time. Reduction is a gain of electrons by an atom or ion, which means that the oxidation number goes down or becomes more negative, and this is called, it reduces. Oxidation is a loss of electrons by an atom or an ion, and the oxidation number goes up. Or becomes more positive, and we say that it oxidizes. A helpful way to remember this is Leo says gur. Some people say Leo the lion goes gur. I just say Leo says gur, which means loss of electrons is oxidation, and a gain of electrons is reduction. Oxidation and reduction happen because of the desire or competition for electrons in a chemical reaction. Species prefer to either gain or lose electrons in a chemical reaction. So we can't just have one of them going on, because what one loses, the other one has to gain, so that we can conserve charge. Just as we have the law of conservation of mass and energy, we have the law of conservation of charge. So our charges on the left side of the reaction must equal the charges on the right side of the reaction. Oxidation and reduction are mutual, or as I said before, simultaneous reactions, and one cannot happen without the other. If one atom gains electrons, then there must be another atom that will lose the electrons. This is called a green chunk experiment. If I take aluminum and I put it in a copper chloride aqueous solution, okay, this is a blue solution, and I will do this demonstration for you in class. If I take aluminum and I put it in a copper chloride solution, and this is solid, remember that a reaction can take place according to Table J, because aluminum will push out copper because it is above it. You know that whole let's not lower our standards scenario I gave you. So you're going to produce aluminum chloride. So we have to look up our charges. This is +3, -1. So when I drop and cross, it's going to be AlCl3 and what's left is plain copper. Now we have to balance this. I have 2 Cl's here and 3 here, so that's an uneven number, so I need the least common denominator. So let's put a 2 here, so 2 times 3 is 6, and a 3 here, so 3 times 2 is 6, which means that I need 2 aluminums here, and I need 3 coppers there. Now, let's finish assigning oxidation states to these. I already assigned the +3 and the -1 to the chlorine. Over here, I've got copper that is +2. This 2 came from here, and my copper, my chlorine is -1. Any element, this is one of the first rules that we will learn, any element that's by itself, including Brinkelhoff. So if I have H2, O2, I2, any of Brinkelhoff, okay, they're considered in the free or standard state, they get assigned a 0. So these get assigned a 0. So I just want you to see that my aluminum is going from a 0 charge to a +3 charge. Now think of aluminum. Aluminum has 13 protons and 13 electrons. So if it gives up 3 electrons, it will have 13 protons and 10 electrons, which will give it +3. So this went from 0 to +3. It lost electrons, so when it loses, it becomes oxidation. So technically, aluminum is oxidized in this reaction. And I'm going a little bit above and beyond, just laying some groundwork. Copper went from +2 to 0. So it gained electrons, because when you gain electrons, you become more negative, because you're gaining negative charge. So the copper is reduced. We'll go over that again. One way that we can begin to identify a redox reaction is to inspect the oxidation numbers, as I was just saying, from the reactant side to the product side for every element that is involved in the reaction. Oxidation numbers are used to track the movement of electrons from the reactant side to the product side. The oxidation number, or the oxidation state, is either positive, negative, or, as I just suggested, in some places, neutral, meaning it's assigned a 0 if the element is in the free state. Identify how many electrons are being lost or gained by an atom or ion when they form bonds. These are the possible oxidation numbers for carbon, and normally we're using the top one unless otherwise stated. So, trick 1. Single replacement reactions, which we've been talking about a little bit lately, single replacement reactions are always redox. But remember that the element that's pushing in has to be more active than the one it's pushing out. So Zn is above H on table J. It can push H out, which means we're going to form ZnCl. This has a +2 charge, -1 charge. I get these from the periodic table. Drop and cross, so it's ZnCl2. And remember, I can't just write H. It has to be H2 because it's diatomic. So then we have to balance the equation. I've got 2 Cl's, so I need to put a 2 here, which gives me 2 H's, and then I'm balanced. If I were to look at this and assign the remaining oxidation charges, zinc is by itself, it's 0, H is +1, Cl is -1. I already did +2, -2, and H2 is part of Brinkelhoff, it's in the free state, so it also gets a 0. Notice here that Zn and H2 are by themselves on one side and then bonded on the opposite side. Double replacement reactions are not redox. For example, Na is +1, OH is -1, H is +1, Cl is -1. When I regroup, I have NaCl and I have H2O. Na is +1, Cl is -1, H is +1, and I forgot this. This is -2 for the oxygen, -1 for the H, and oxygen is -2. So you can see that none of the oxidation numbers changed at all. Therefore, we do not have oxidation. Okay, I'm going to show you a quick little video that's going to give you an overview, a little bit about what this unit is about as far as oxidation and reduction, and we'll pick up with the rules in our next lesson.
Displacement reactions are among the most common redox reactions. For example, a metal in a compound can be displaced by another metal in the uncombined state. When metallic zinc is added to a solution containing copper-2 sulfate, it displaces copper-2+ ions from the solution. Zinc reduces copper-2+ ions by donating 2 electrons to it, producing copper metal and zinc-2+ ions in solution. Note that copper metal is depositing on the zinc bar. Also, during the reaction, the solution loses the blue color that characterizes the presence of hydrated copper-2+ ions. Let's zoom in to view the reaction on a molecular level. Zinc atoms enter the solution as zinc-2+ ions, losing 2 electrons. Zinc is oxidized. The electrons are gained by copper-2+ ions, which are converted to copper metal. Copper-2+ ions are reduced. Similarly, metallic copper displaces silver ions from a solution containing silver nitrate, AgNO3. Each copper atom reduces 2 silver+ ions by donating 2 electrons. Note the silver metal is depositing on the copper wire. Also, during the reaction, the solution turns blue due to the presence of hydrated copper-2+ ions. Let's zoom in to view the reaction on a molecular level. Copper atoms enter the solution as copper-2+ ions, losing 2 electrons. Copper is oxidized. The electrons are gained by silver+ ions, which are converted to silver metal. Silver+ ions are reduced.
Okay, that's our lesson for tonight. Stay tuned for lesson 2 next class.